Hi everyone, it's my pleasure to talk today about CFML, a tool for the verification of OCaml programs. By verification, I mean establishing the functional correctness of the code, including termination, and possibly also including asymptotic time bounds. The verification is interactive. CFML is embedded in the Coq proof assistant. Targets OCaml programs. So why OCaml? Not just because it's our favorite language, but also because OCaml features a clear semantics which makes reasoning about programs relatively easier. Which programs are we talking about? CFML has been so far mostly used for verifying data structures and classic algorithms, which are essential building blocks for larger programs, and thus it makes sense to get started with those. CFML has been developed for over the past 10 years, started initially by supporting verification of purely functional code, and then quickly extended to support the verification of effectful code thanks to separation logic. In 2015, François Potier helped me develop an extension based on something called time credits for verifying asymptotic time bounds. In 2017, Magnus Myrin, developer of CFML, got interested in CFML, and he invited OCaml Guénaud to port the ideas of CFML into HOL. Not just OCaml successfully ported the ideas, he also extended the framework with exceptions and provided an axiom-free presentation of the approach. Recently, we've been working on extensions, including the theory of read-only permissions, support for big O reasoning, and an extension of time credits called possibly negative time credits. I've been also working recently on CFML 2.0, which I'll talk about later in the talk. All the development of CFML have been accompanied with case studies, ranging from purely functional data structures from Okazaki's book to graph algorithms such as Dijkstra's algorithm or DFS. In 2016, François Potier verified a hash table implementation, essentially the one that's in the standard library of OCaml, and also showed how to verify fold higher order iterators in our cascade. We've also been verifying data structures, including the time bounds. This includes the union find data structure with the inverse argument bound, a variant of finger trees called bootstrap chunk sequence, which I've been developing, proved bound for the C for error testiness, and also verified an incremental cycle detection, which I'd like to say a few more words about. So the problem is to you have a graph, you keep adding vertices and keep adding edges, and you want to detect the first moment at which a cycle appears in the graph. Tarjan and his co-authors recently proposed a new algorithm that significantly improves over the state of the art. At a high level, you organize the vertices in levels, and you combine forward DFS with partial bounded backward DFS that are limited both in the number of edges that they can traverse and the levels that can be traversed. So it's quite a fancy algorithm, and OCaml Guénaud implemented this algorithm in about 200 lines of OCaml code, relatively dense code, and it was able to prove the full functional correctness of the code. And together with Jacques-Henri Jourdan, he established the amortized complexity bound for this algorithm. The code today of OCaml is implemented in the Dune build system and runs in production. So today, I'm not going to present one of these fancy case studies. I'd like to give a precise description of the workflow of how it is to work with CFML. And for that, I'll consider simpler case studies. So first example I'll present is a mutable queue. And then I'll present two variants of the union find data structure, one with arrays and one with pointers. The rest of the talk, I'll discuss also the limitation of CFML. I'll give an overview of CFML 2.0, and then discuss perspectives, how CFML fits into the bigger picture of program verification. So let me move on to the first demo. Consider a mutable queue representation with two lists, the front list and the back list that stores the element in reverse order, and a size field so that we get an interesting invariant to specify. So to create an empty queue, you can just allocate a record. To push an element, you push it in the back and you increment the size field. And to pop an element, you have to first make sure that the front is populated if the queue is not empty. And then you can actually pop an element from the front and decrement the size. We'll also be presenting the transfer function, which transfer all the items from one queue into another queue, and that has an interesting specification from separation logic perspectives. So the first thing to do is to feed this file to the CFML compiler. And what CFML produces is a file called mutable_q_ml.v. This file is not meant for human consumption. It is only low-level generated syntax. What it does, it binds a name for every function defined in the ML source code. And it also produces as one axiom that corresponds to what's called the characteristic formula associated with the code. So the characteristic formula of a function is a description of its semantics in terms of logical operators. And this characteristic formula is going to be used for establishing specification in the interactive proofs, like I will show you in a minute. So the proof is actually, it carries out in this file, in which I load the generated file by CFML. And the first thing to do is to specify the representation predicate. That is the relation between the representation in memory of the structure, which is a record made of front field, a back field, and a size field, and the list of items that it represents. So the list corresponds to the front concatenated with the reverse of the back. And also the representation predicate captures the invariant. Here we have to assert that the value n stored in the size field is equal to the length of the list L. So this predicate is defined as QLQ, and in the specification there's this handy notation using a tilde arrow. Q points to Q of L. So Q here is the address of the queue in memory. Before we get started, we need to state an unfolding lemma and a folding lemma, which are convenient and are exploited by the xopen and xclose tactics that you'll see used in the proof for folding and unfolding the representation predicate. So let's get started with the verification of the create function. So create is specified using this app notation that comes with CFML. It specifies the function f and two arguments x1 and x2, a precondition h and a postcondition h prime, in which the result produced by the function is denoted as r. So in the case of create takes a unit argument, an empty precondition, and it returns a q that is represented as that represents the empty list. So how to carry out the proof? Always the proof, and make sure that have a look. The code here is polymorphic in the type A, for God's sake. So to carry out the proof, begin with the XCF tactic that essentially exploit the characteristic formula associated with the code. And what appears here is in the proof obligation is a precondition, the postcondition from the specification, and here the code of the function in some funny syntax. Here it denotes the allocation of a record. So we can use the XApp tactic. All the X tactics are provided by CFML. The XApp tactic to reason about this call, and we can introduce the name of the result. And at this point, our current state is described by the record, and what we're aiming for is the Q predicate. So all that remains to do is to fold the Q representation. At this point, we have to verify the invariance. So 0 is the length of the empty list, so we can obtain that by normalizing the list and checking the map. And in this one, now we can see that our current state has been folded into the form that appears in the post condition. So essentially we're done here. And the xsimple tactic handles the simplification. You may wonder what the \gc is here. It's useful for getting rid of allocated data that's no longer needed in the post condition, but you can forget about that for now. So here is the specification lemma. What we're going to do is to register it together with the function so that subsequently in the script, whenever there's a function call to create, the specification of create can be automatically exploited. So let's look at the push function here. So push, recall that it extends the back and increment the size. So the first thing CFML does is to normalize the code, but in a normal form, by naming all intermediate sub-expression. And that's why you'll see some generated names like x0 and x1 appear in the characteristic formula. So push takes a queue and it returns unit and updates the queue in place to extend its representation with an x at the tail. So let's go for the proof called xcf. I can reason about the call to app using xapp, and then it doesn't work. Why? Because I'm in a state where I have a folded view on the queue, and I need to open the representation predicate and pull into the context the variables describing the field, frn, as well as the invariant on I and L. Now at this stage, I'm able to see the representation predicate for the record, so I can read into the backfield. Now I can update the backfield with the result of the cons operation. Not quite. All right, because I need first to substitute away this x0. And it's actually very common to substitute away the result of an operation. So the xapp static is a shorthand for xapp with a subst. So now I can do the same thing, reason about the write. So now the back is updated, it's got x cons r. Now I can read in the size field, substitute, and write the new value into the size field, which evolves from n to n+1. The result value is unit. I can fold back the representation predicate for the queue. I need to justify here the fact that the length is, there's a subst missing. Justify that the length is match up. And here again, if I substitute L in and normalize the list, I can check that the result is as expected. I forgot to say that the nx is a shorthand for ++ x cons nil. Okay, so we're done with the push function here. Remains the pop function. So I'm not going to show all the details of the pop function. There are two interesting features. One is the specification. It's specified as a partial function. It only applies when the list representing the queue is not nil, meaning that the queue is not empty. And the result is a value x, such that L decomposes as x cons sum L prime, and where L prime is a new state. So L prime is quantified in the post condition here. What's interesting in the proof is that there is an interesting cut point here. After the first phase, we've updated the front and the back field in such a way that the front field is no longer empty. So this appears in this intermediate specification here that's given interactively in the proof script, where we say there exist f prime and b prime, which are the null contents of the front and back field, so that the representation of L has not changed and f prime is not nil. And from there, when we get to the match, we have at hand the hypothesis that f is not nil. So when we do the case analysis on whether f is nil or not, we will immediately go into the second branch where the remaining of the code is taking place. Like I said, I wanted to say a few words about the transfer function. So transfer is a function that takes two queues that are assumed to be disjoint from one another. That's captured by the star separation logic. It returns unit and updates the state by making Q1 become empty and Q2 as its content extended at the back with the contents of the first queue. The proof of the while loop can be carried out using a loop invariant, just like in our logic. Though there is another technique for reasoning about while loops, which consists in carrying out proof by induction, and that's what I'm doing here. The idea is that if you specify the behavior between a given iteration of the loop and the last iteration of the loop, and then you can reason about one step of the loop and invoke the induction hypothesis for reasoning about the behavior between the next iteration and the last iteration. And this approach, although it's not needed here, has a benefit that you can invoke the frame rule for putting on the side the some pieces of resources that are not needed to the rest of the iteration. Okay, and then we're done with this proof. The unified data structure is represented using an array that maps every node to its parent node. Initially, every node points to itself. Every node is a root in an independent component. And we have the standard implementation with a find function that works out the parent links until we reach the root. The test for whether two nodes are in the same component, comparing the roots, and the union function that, if needed, sets up a link from one root to the other root. So again, I provide this file to the CFML compiler, and if I go into the code proof, before I start actually reasoning about the code, I'm going to develop a theory of union find. That is a theory of what it means for having a path between a node and a root in a reverse forest. So this development is generic and will be shared by the pointer-based implementation of union find that we'll see in a minute. So here, P is a representation of the graph, that is of the reverse forest that we have at hand, and it's a map that maps every node to its parent. Rep P x z asserts that in that graph, z is a root of x, and is defined inductively. Either a node is its own parent, in which case it's a root, or if x points to y and y has root z, then z is a root of x. And then the main invariant is captured by the roots predicate, which relates the map P, the parent map, with the function R, which is a function exposed to the client of the data structure, and it is a function that binds every node with its root directly. So the idea is that for every node in the domain of the map P, x should have a path down to the root of x. So this file contains first an induction principle on the height of the rep derivation. That's what we use for the justifying the termination of the find function. It contains a bunch of lemmas asserting well-formedness properties of the rep predicate, also basic properties of the roots predicate, mostly to justify that nodes are in the domain and point and parent and roots are in the domain. And most importantly, it contains a bunch of lemmas establishing the fact that the roots invariance is preserved by the operations on the union find data structure. So first, if you have a map P in which every node is its own parent, then the roots invariant is satisfied. Second, for linking, there is this predicate link that we'll see in specification. So link RXYZ asserts that all the nodes in either the component of X or in the component of Y now are updated to have Z as new root. And this roots link lemma shows that when you set up a link from the root of X to the root of Y, then you indeed update R according to this link function. And finally, there's a lemma for justifying compression. If you take a parent map and you update any node to directly point to its own root, then all the invariants will be preserved. And for the pointer extension implementation that we'll see later, we'll also have an additional lemma for justifying that when you add a fresh node that extends the domain, all the invariant remains preserved. All right, so once this file is set up, we are ready to dive into the verification of the code. All we have to do is to define the UF predicate. So UF captured the fact that an array T implements an instance of union find for n different nodes, and a root relation, a root function described by R. UF is defined as follows. It quantifies the map, parent map P, which is a contents of the array T. And then there are two invariants. First, the domain of P should be exactly the range 0 to n minus 1. And second, the roots invariant that I introduced in the previous file should relate P and R. So again, P corresponds to the implementation of the parent links in the code, while R is a logical representation of the structure directly relating nodes to the roots, and that is what is exposed to the user. Let me read a couple of specifications. So the specification of create expects a non-negative number n, an empty precondition, and it builds a fresh instance of union find in which every node is its own root. The specification of find takes a valid index x and an instance of union find, and it returns R, which is equal to the root of x. It also returns the instance of union find, which is unchanged, although internally there might have been some path compression going on. So because this piece of precondition is copied in the post condition, that's a frequent pattern which I have syntactic trigger for. So I write inf instead of pre, and that means repeat the precondition into the post condition. One thing interesting in the proof of the find specification is the induction on the depths of the derivation of the proof that describe the path from x to its root. And this is what justifies termination of the find function. For testing, the two nodes are in same component, the post condition asserts that the Boolean value b that is returned is characterizing whether Rx and Ry are equal. That is, if x and y are in the same component, have the same root. And the union function, most interesting here, takes an instance of union find and updates it to a new state where R is now described as according to this link relation which I introduced earlier. So if we look into the code, let's go back to the code. So we have two calls to find, and then depending on whether they are in the same component or not, we might need to update a link from R to S and then return the component. So we first reason about the two calls to find, then about the comparison, whether it's true that the root is the same. In the first case, we can unfold the invariant, and we have to reason about this piece of code here. So we had the fact that the root of x in the domain, and then we can reason about the application, return, and discharge the proof obligations associated with the invariants. In the other case, there is no update performed. All we have is to justify that the link operation is the identity when the two roots are already in the same component, and there is a lemma for that. So let me now move on to the third case study, which is a variant implementation of union find that is based on pointers and that includes rank information for performing union by rank. So here, every node is a reference on either root or a link to a different node. Initially, you can create nodes by creating fresh references with root 0 as contents. Find follows the links until reaching a root. Same simply compares using physical equality the two roots. And the union operation, once it's found the roots of x and y, if they are distinct, will compare the ranks and set up a link from the root with smaller rank to the root with higher rank. And it returns the identity of the new root for the merge component. In case the ranks are equal, the resulting root needs to have its rank increased by 1 unit. So that's an additional complexity to handle. So when we go to the proof, things are a little bit more complicated now, because we have to describe a collection of references, disjoint references that are scattered in memory. So we're going to use the group predicate provided by CFML to describe this group of references and bind M, where M is a map that's going to be describing this group of references. M binds the location of each reference to its content. And we call that the content of a reference is either root or a link to Y. And we'll use this interpretation function called parent to say that the parent of a node at location X and content C is either X if the contents is root, and it's Y if the contents is linked to Y. So in this UF predicate that features the group, I packaged all the invariants into a separate predicate called inv. So inv exposes the domain D, which is a set of valid locations in the instance of a union find. And this D should match the domain of M. The second important invariant is the roots relation, which is the same as before, except that now it's relating R with the result of applying the parent function to M. And this is indeed a map from location to locations. The third invariant is for convenience. It asserts that outside of the domain D, the roots, so R of any node is equal to itself. And the fourth invariant is important. It asserts, it's defined here, it asserts that for any node that's in the domain, if the node is as contents link Y, then Y must be distinct from X. Otherwise, if X was a root, it should have stored as contents, it should have as contents a root and not a link to itself. So once we've defined all of these invariants, we are ready to carry out the verification of the code of the pointer-based implementation of union find. So just set up a few ints. I'm not going to go through all the details. The only thing I want to point out is that for every lemma establishing a specification, I actually pull out into a separate lemma the main mathematical result that justify the correctness. That is the preservation of the inv invariant. So for example, for create, here it shows that adding a fresh node X to the domain and assigning it to root in the 0 in memory preserve the invariants. Likewise, for pass compression, if we extend if we get a node to be mapped directly to its root, provided that it was not already a root, then all the invariants are preserved. And this lemma leverages the roots compress lemma, which was establishing a result similar for roots invariant, but here it's doing more because it's establishing the preservation of the invariant for the 4 invariants that we have, and not just for the roots invariant. Okay, we do so all the way to the union specification, and there, what's interesting in the proof of union is that the two symmetric case, whether you link in one direction or the other direction, are handled by the same lemma about linking, just invoke on different arguments depending on the direction. So this concludes the proof of union find, and this concludes the demo. So let me go back to the slides. Let me talk about the limitations of CFML. So CFML does not cover all of the OCaml language, obviously. It's restricted to essentially the CAML Lite fragment plus basic support for functors. The support for functors is limited essentially because I'm mapping OCaml functors to Coq functors, but Coq functors are much less are much more limited than OCaml ones. That's certainly something to find a way around in the future. OCaml, there's a number of OCaml features that are not yet supported, but could be easily handled, I believe. So that, like the record with syntax, the possibility to reason about named argument for constructors, label, optional arguments, and exceptions. And there are a bunch of features that are not handled yet, and it's not clear how to deal with them. For objects, whether we should use an encoding maybe, but is it really worth dealing with objects knowing that they're not so much used in practice? For lazy evaluation, maybe some encoding also is possible, but for the moment I simply ignore the lazy keywords. The effectful when clauses don't have a really clear semantics in OCaml, so at the moment I'm restricting it to when clauses for pure Boolean expressions. Polymorphic variants, there's no such thing as extensible inductive definition in Coq, so I'm not sure how to map them in a modular way in Coq. And recursive values, handling them will require non-trivial changes to the semantics and complication with co-inductive definitions, so that's something I've left aside. The two limitations associated with Coq itself. So they appear when translating algebraic definitions into inductive definitions. Consider, for example, a tree with leaves and nodes that are made of list of subtrees. You can translate that in Coq, that's perfectly fine. But now if you fancy having an intermediate type for the branches as a shorthand for tree list, then you can no longer map this to Coq because there's no such thing as having recursion between inductive definition and plain definitions. Another limitation, still based on the same example, is if you want to replace the list constructor with an abstract constructor for sequence, coming from an abstract module, and if you map that to Coq, then the positivity checker of Coq complains that it's not able to verify that tree appears in positive occurrence. For that, we'll need an extension of Coq with positive annotations on type constructors, but that's something that does not exist at the moment. There are two features that are not integrated in CFML, but we've been working on. The first one is temporary read-only permissions. So that is essentially quite important in practice. A concrete example is the concatenation of two arrays. So you have an array A1 and an array A2, and the function produces an array A3 whose contents is a concatenation of the first two. And the problem with this specification is that you cannot concatenate an array with itself. Indeed, you cannot provide two copies of the same array in separation logic. The solution is to introduce read-only permissions. Read-only permissions are duplicatable, so you can make two copies of it if you have one. And also, interestingly, they are implicitly returned in the post condition, so specifications are more concise because you don't need to repeat the fact that the arrays from the precondition into the post condition. Another feature is a surface language we've been working on in the context of the vocal project. I'll go very briefly over this and point to the pointer for details to the paper for details. Imagine that you have a function that takes 4 points and an integer and returns 2 points and an integer. A typical separation logic specification for it would involve quantifying tons of variables and involve having representation predicates all over the place. It's, in essence, can be specified in a much more concise way by exploiting two ideas. The first one is you should associate a representation predicate by default to every type. And the second is you can leverage keywords such as requires, ensures, modifies, and consumed, keywords that have proved very useful in other proof tools. As we show in the paper, you can formalize the idea of a specification in a much more concise way as shown before, and have a translation from that surface language into an explicit separation logic specification from which you could carry out proofs in Coq. All right, now I'll move on to the next third part of the talk and say a few words about the key aspects of CFML 2.0. So there are currently 4 ingredients: a deep embedding of the core ML language, a shallow embedding of separation logic, pretty much the same as is currently in CFML, a characteristic formula generator that is no longer as an external tool but presented as a Coq function that computes within Coq, and a collection of tactics like before, but with new features and much more simplified implementation. So let me say a few words about the first 3 points. The deep embedding consists of describing the grammars for values and terms as inductive definitions, and that's done on a non-typed language. The memory model is essentially a finite map from location to values, and the semantics is described using an inductive definition in Coq, capturing a call-by-value substitution-based big-step style semantics. The separation logic is described using heap predicates that are defined as Coq functions. That is, for example, h1 star h2 is defined as a predicate that holds of a heap h, if and only if this heap can be split in 2 parts, 2 disjoint parts, one satisfying h1 and one satisfying h2. The separation logic triples are defined in 2 stages. First, the notion of OR triple is defined with respect to the big step semantics. So HTQ asserts that in any state satisfying the precondition, the evaluation of the term T in a state S produces an output value V and an output state S prime that together satisfy the postcondition. And separation logic triples are defined on top of them, those by quantifying over the rest of the world, H prime, and asserting that the triple made of H star H prime and Q star H prime is a valid OR triple. With respect to that definition, one can derive structural rules, such as the famous frame rule, or rules for reasoning about term construct, such as the rule for sequence, for example. So CFML is based on characteristic formulae, which are a form of weakest preconditions in CFML 2.0. So in traditional law logic, weakest preconditions are applied to code annotated with invariants and specifications. And they produce relatively bulky formulae, which are meant to be processed by SMT solvers. On the contrary, characteristic formula target separation logic and have to handle the frame rule, which is not syntax directed. It applies to unannotated code, that is, the code without any specification or invariants. And the goal is to produce linear site formula, which can be read by the user inside the Coq proof assistant. So how to deal with the 3 challenges? First, to deal with the lack of annotations. Characteristic formula quantify intermediate invariants existentially. And for reasoning about function calls to functions whose specification is unknown, characteristic formula simply refer to the triple. To ensure scalability and readability, characteristic formula are generated following the structure of the code recursively and leveraging auxiliary definition and notations for making the formula display somewhat like the source code. And to support the frame rule, there is internally a predicate transformer that's added at every node of the generation of the characteristic formula that allows to apply the frame rule where needed and that can be freely discarded when the frame rule is not needed. So in CFML 1.0, characteristic formulae are produced as axioms, and they do leverage the type information available, which is very convenient for the user. In CFML 2.0, on the contrary, characteristic formulae are computed as a Coq function, which is more trustworthy, but makes it almost impossible to exploit the type information. So that's putting a bit more burden on the user that in some places have to reconstruct type information during the proof. What I'd like to do is to get the best of both worlds by producing in CFML 2.0 characteristic formula from the typed AST, just like before, and at the same time produce evidence that these formulae are correct. And to achieve that, the idea is to translate the source code into the deep embedding, compute using the coq function that produces the characteristic formula for the untyped code, a non-typed characteristic formula, and then show that the type-aware formula that is generated in point 1 is derivable from that untyped formula. The idea is that the semantics of an untyped program is strictly more general than its type, the semantics of the type program that corresponds to it. If you're interested in learning more about CFML, you can find information in the course notes that will be soon released as a volume from the Software Foundation series. So it's a course where every definition, every lemma, and every exercise is formalized using the coq proof assistant. You can find currently the course on my webpage. I'd like to conclude this talk with perspectives, first on the verified compilation chain, on language extensions such as arithmetic and concurrency, and on verified algorithms. So the grand challenge in program verification is to establish end-to-end proofs going from high-level specifications down to the hardware. CFML 2.0 relates high-level specification to the semantics of deeply embedded code. This deeply embedded code can be related to that of taken as input by a verified compiler, such as OCaml, that relates deeply embedded code down to machine code. And this machine code can be connected, potentially, with the semantics of the hardware. So there's been ongoing work on developing specifications for the hardware instruction set, and there's ongoing work for relating OCaml semantics to these semantics. Of course, they remain to prove the hardware correct, but that's another story. So with just the 3 points, if they get connected one day, then we'll achieve this end-to-end tool chain, compilation chain. Another aspect that's interesting is the work on SMT coq, which could produce traces from SMT solvers that could be validated in coq, and that will be very helpful for carrying out the proofs in CFML2 in a very trustworthy way. Now, real programs generally involve numbers, I/O, and concurrency, which are features that are not well supported in CFML at the moment. Machine integers, the main challenge is to avoid polluting specifications and proofs with numerous details about overflows. There's an interesting piece of work I'd like to mention by colleagues of mine, which is how to prove the absence of integer overflows without effort, essentially. So there are a number of cases where, for example, if you use an integer to measure the size of a tree, you know that this size will never blow up because it will just take too long or consume too much memory to build a tree that is bigger than 2 to the power 264. There's been a lot of work on semantics of floating point arithmetics, great tools such as the Flock library or the GAPA tool. I would like one day to work on the integration of those into CFML. The OCaml team has been working on verified I/O, both for terminating and for non-terminating programs, so I can point to this work. And for concurrency, the IRIS framework provides a very general concurrent separation logic. And at this ICFP, there's a paper on an instantiation of IRIS targeting the semantics of multi-core OCaml. So one day it will be interesting to see how this can be merged with the techniques of CFML. Third perspectives regarding verified algorithms. So data structures in classic algorithms are pervasive in large programs. So it makes a lot of sense to ask the question, how much of a textbook such as Introduction to Algorithm has been verified so far? And this question has been addressed by Tobias Nipkow and 2 of his students in the recent months. They wrote a survey paper about it. Tobias' team is making fast progress on verification of algorithm using the Isabelle refinement framework that features time credits, like in CFML. So if you want to read the survey, make sure to read it soon before it's completely out of date. Wouldn't be surprised that in a couple of years, Nipkow announces the complete verification of the Introduction to Algorithms textbook. one important piece of work that they did is the formalization of a generalized version of the master theorem. So you probably know about the master theorem for solving recursion. There's an extension of it that's less well known by Accra and Bazzi, and a very clean description of this result by Tom Layton. It's only 2 pages long. It's really amazing how general this result is. And it's been formalized entirely in Isabelle Hall by Manuel Herbal. Finally, I'd like to point out the challenges with multivariate big O analysis, that is big O when several variables are involved. None of the textbooks on algorithms give a proper definition of what it means to write a big O with different variables in it. It's actually completely non-trivial, and the only work on it that we could find was course notes by OL. So in OCaml Guénaud's PhD thesis, we've been working on developing a formalization of the multivariate big O analysis. But yeah, there are very interesting challenges there. All right, as closing word, I'd like to take a look at how long the road is. In programming languages, new features take years to emerge. Just think about multi-core CAML, for example. While in program verification, new features take decades to emerge. Just look at the timeline for program logics. It's been 15 years, more than 50 years since the introduction of Floyd-Hall logic. It took about 30 years to develop separation logic. And 20 years after, we're still, like every year, discovering new features of separation logic. If you look at proof assistance, it's about the same. It's been more than 50 years since the first proof assistant was devised. The calculus of construction at the heart of Coq is 35 years old. And Coq exists in a modern enough version that you could carry out CFML proofs for almost 20 years now. So there are 2 ways to look at this timeline. The pessimistic way is to say, oh, it took 50 years to develop all this. It's going to be another 10 or 20 years before program verification becomes a routine exercise. Or you can take the optimistic view and say, we've been working on these great tools for 50 years. Now we just need to wrap it up, and in a year or 2, we'll be able to verify all programs. I believe there's some truth to both of these statements. Probably in a couple of years, we'll be able to verify relatively easily large classes of programs. And at the same time, there will remain large classes of programs that will not be within reach before within the next decade, I believe. Anyway, only time will tell. I'd like to thank Leo for giving me an opportunity to talk about CFML, and I'd like to thank you all for your attention.